Well, first I'd like to thank Al and Mike and David for inviting me to this conference. It's a real pleasure to be back on the Northwestern campus. Some of you may know I was a professor here from 1965 to 1981 before I went to Hawaii. And I also would like to thank Beth Herbert for all the work she did in organizing the conference. Now, in light of the fact I'm talking about global warming, my slides are in hot pink to emphasize that point. And the title is Global Warming, Fact or Fiction? And personally, I and many others, including Wally Broker at Lamont Doherty Observatory of Columbia University, feel that we're sort of dealing with a dragon here, the climate dragon. This is us, and we're perturbing this dragon by putting greenhouse gases, gases that absorb outgoing Earth radiation, into the atmosphere of gases of carbon dioxide, methane, nitrous oxide, tropospheric ozone, which is actually manufactured in the atmosphere, and the synthetic gases, the chlorofluorocarbons, gases that contain chlorine, fluorine, carbon, and hydrogen. And what we're doing is putting these gases into the atmosphere owing to human activities, and we're perturbing this guy. And sometime he's going to let loose a real firebolt, and we're in for a big surprise. Now, we've always had what is known as a greenhouse effect. We've always had gases in the atmosphere like carbon dioxide, methane, nitrous oxide, and tropospheric ozone. These gases absorb outgoing Earth radiation and lead to heating of the surface of the Earth. And what you see here is the incoming solar radiation, its wavelength spectrum, and that is pretty intense radiation, containing a reasonable amount of shortwave ultraviolet radiation, visible radiation, and a little bit of infrared long-wave heat radiation. The average wavelength of that radiation is about 1/2 of a micrometer. That is 1 × 10⁻⁷ meters. That radiation comes into our atmosphere, enters the top of the atmosphere, and the first thing that happens is that it's absorbed by oxygen in the atmosphere, oxygen gas, and then by lower down in the atmosphere by stratospheric ozone gas. But the energy keeps penetrating our atmosphere, and as it gets deeper and deeper into the atmosphere, it reacts with very small micrometer size, really tiny guys, particles, and reacts with clouds and is reflected, absorbed, and re-radiated back to space. However, about 45% of this incoming solar radiation reaches Earth's surface, where it then drives processes like evaporation and so forth, but is re-radiated back to space as relatively long-wave outgoing Earth radiation with an average wavelength of 10 micrometers, 10 × 10⁻⁶ meters. That is the radiation that is absorbed by these greenhouse gases in the atmosphere. The natural greenhouse gases of carbon dioxide, I'll mention them again, methane, nitrous oxide, and tropospheric ozone. And in today's world, the synthetic gases that have entered the atmosphere, the chlorofluorocarbons. So Earth has always had a natural greenhouse effect. And that greenhouse effect warms our planet by about 33 degrees. Without this greenhouse effect, the planet would be minus 18 degrees centigrade. Pretty cold place to be. Now these are the greenhouse gases, a little more. I'll show you some data. I think it's kind of necessary to see these data. This is the greenhouse gas carbon dioxide, CO2, greenhouse gas methane, CH4, the greenhouse gas nitrous oxide, N2O. That's laughing gas, by the way, that some of the older people, including myself in the audience, might have had to put you to sleep when they pulled a tooth. These are the synthetic chlorofluorocarbons. Now, those gases are a potent greenhouse gas in the lower atmosphere, it happens that these are the culprits in the destruction of stratospheric ozone. These are synthetic compounds, and they're produced by industrial and other activities of humankind. Tropospheric ozone and water vapor, which, by the way, is the most potent greenhouse gas in our atmosphere. This column shows the concentrations. Just this year, we reached 380 parts per million by volume of the greenhouse gas carbon dioxide in the atmosphere. The late pre-industrial level was 280 parts per million. So, carbon dioxide in the atmosphere since approximately 1850 has risen 100 parts per million, or about 35%. Now, I'm not going to go all through these numbers, but these are the present concentrations. This shows the pre-industrial 1850 concentration, and also the concentration at 18,000 years ago at the end of the last glacial maximum, which in Illinois is called the Wisconsin glaciation. And this shows the concentrations at the so-called LGM. This shows the annual rate of increase today. Carbon dioxide, for example, is increasing at a rate of about 0.4% annually. And this shows the contribution of the individual gases to the so-called enhanced greenhouse effect, which I'll talk about in a moment. So the carbon dioxide is responsible for about 55% of the enhanced greenhouse effect over the last 150 years. Now, we are totally out of the realm, the environmental realm of the past 420,000 years. And you'll soon, those of you that do read the scientific literature, there soon will appear papers that take what you see here, and I'll explain this in a moment, the Vostok ice core data, back to 800,000 years. And we see much the same trends that we see in this 420,000 year record. Now what this is a record of various properties of ice as drilled at the Vostok ice station in Antarctica. They drilled a 3.8 kilometer core and used that ice to determine certain properties of the ice, which give us an index of, for example, changing atmospheric carbon dioxide through the 420,000 years of Earth history. And I want to really look simply at this one. We don't have time to look at everything here. What I would like to point out, that notice that carbon dioxide for the last 420,000 years up to the Industrial Revolution of 1850 varied between, for this whole period of time, 180 and 280 parts per million. There are now 380 parts per million in the atmosphere. So we are totally out of the environmental realm of the greenhouse gas concentration of CO2 in the atmosphere. Notice the very reasonable correlation between carbon dioxide and temperature. When carbon dioxide is high, relatively high, during the past 420,000 years, temperature has been relatively high. Sometimes the temperature signal precedes the carbon dioxide signal, sometimes it's in the reverse. Now, the consensus opinion today is that there is an enhanced greenhouse effect. Earth is warming, and we are perhaps headed for a super interglacial glaciation. What you see here are the two interglaciations and two glaciations and the future glaciation of the next couple thousand years ago or so into the future before we enter it. And you'll see the warming here in the last interglaciation, and then as we go from that into the last glaciation, the temperatures fall, and then since 18,000 years ago, the temperature has risen, but somewhat irregularly, up to pre-industrial temperature levels, And then with the addition of greenhouse gases from human activities, what we're concerned about is that we will have a warming that we will not have seen in the last 420,000 years. Hence, the next glaciation will actually be farther into the future because of this warming due to human activities. Now, there's another side of the coin, and this is somewhat disturbing. This comes out of the Wall Street Journal. Science has spoken. Global warming is a myth. They actually used two scientific conclusions in the wrong manner. What they correlated here is the change in the sunspot record, therefore the amount of solar radiation reaching the planet, the so-called solar cycle, with temperature over the last 100 years or so, and showed a good correlation and said, this is a causation, and that's incorrect. The other thing they did was to look at the total tropospheric temperature record, and they saw a slight cooling now. Now that's the interpretation of that. There's a misunderstanding there also. Indeed, the whole troposphere does cool slightly, but the surface still warms. Now, the enhanced greenhouse effect. The Earth is due to enter another glacial stage in a few thousands of years. I've mentioned that. The Earth warms slightly from 1850 to 1940. It then actually cooled slightly, very slightly, from 1940 to 1970. Since 1970, Earth has warmed relatively rapidly, but erratically. 1998, 2002, 2003, 2004, and probably this year are or will be the 5 hottest years on record. Greenhouse gases added to the atmosphere by human activity since 1850 represent about a 2% addition to the natural greenhouse effect. For those of you that can appreciate the term watts per square meter, the natural greenhouse effect has a forcing of about 125 watts per square meter. The enhanced greenhouse effect amounts quantitatively to about 2.5 watts per square meter. That 2.5 watts per square meter is the enhanced greenhouse effect. It's a greenhouse effect due to human activities. Now, I can't go through all the greenhouse gases because we don't have time, but I would like to look at carbon dioxide as an example of a greenhouse gas in terms of its sources and its concentration in the atmosphere and where it has gone. So the sources of anthropogenic carbon dioxide, that is carbon dioxide from human activities, are fossil fuel burning, including the flaring of gas at oil wells, cement manufacturing, and from those sources, roughly 6.8 billion tons. That's 6.8 times 10 to the 15th grams, 6.8 gigatons of carbon were emitted to the atmosphere in 2004. Deforestation and other land use practices also add carbon dioxide to the atmosphere, and that rate is not well known. It's somewhere between 1 and 2 billion tons of carbon per year. At the beginning of this century, it was probably on the order of about 1.2 billion tons of carbon per year. This shows the growth of the industrial emissions of carbon dioxide to the atmosphere. This is about 80% of the emissions. With only 4.5% of the world population, the United States has accounted for about 1/3 of the industrial emissions since 1950. These industrial emissions include solids, mainly coal, liquids, mainly oil, gases, mainly methane, the flaring of methane gas, and the emission from cement manufacturing. And you can see how these emissions have grown, particularly since the Industrial Revolution of 1850, reaching in the early 21st century 6.8 billion tons of carbon per year. Now, this is the effect on atmospheric chemistry. In 1850, the Industrial Revolution, there were 280 parts per million of carbon dioxide in the atmosphere. We know very well, and that's from ice core records, that carbon dioxide rose continuously during the last 150 years. And owing to our own Mauna Loa record, gas observatory station at Mauna Loa, Hawaii, which is located at about 11,000 feet on the big island of Hawaii, we have a very excellent record of the rise of atmospheric CO2 in the atmosphere since the year 1958 up until present. And you can see concentration here in parts per million of carbon dioxide year from 1958 essentially up to present, and carbon dioxide concentration has risen from 315 to breaking 380 parts per million this year. All of that rise and the preceding 100 years of rise are due to human activities leading to the release of carbon dioxide to the atmosphere. You also see here something that's really kind of neat, I think. It's the cyclical pattern. This is basically the breathing of the northern hemispheric forest. During the summer, when photosynthesis is high, they suck up carbon dioxide and the concentration falls. During the winter, the opposite occurs and the concentration rises. So what you see here is a nice seasonal pattern of the breathing of northern hemispheric forests. Now, where did all the fossil fuel and land use emissions of carbon dioxide go? Well, we know, and we know well, how much has gone into the atmosphere. So the atmosphere has accumulated about 1/2 of the fossil fuel carbon dioxide emissions since 1850. That does not balance all the carbon dioxide that has gone into the atmosphere, so where did the rest go? Some of it, and an important part of it, and Dick Feely will talk about this in the third talk, the carbon dioxide dissolves into ocean water. It's absorbed by the surface seawater. This in itself is important because as the oceans absorb this carbon dioxide, their acidity increases. Their pH falls. For example, if you take hydrogen chloride gas, put it in water, you'll make hydrochloric acid. If you take sulfur dioxide gas and put it in water, you'll make sulfuric acid. When you put carbon dioxide gas in surface seawater, you basically make an acid called carbonic acid, and drives the acidity of the ocean up and the pH down. And this change has already been observed in surface ocean water layers in both the Atlantic and the Pacific. The land also has taken up some of the carbon dioxide. It's taken it up, anthropogenic carbon dioxide, that produced by human activities. It's taken it up by regrowth of temporal forests. For example, New England forests are growing over abandoned agricultural lands. And it's also been taken up by something called fertilization. So as we've added carbon dioxide to the atmosphere, and as we've added nutrients to the Earth's surface, owing to both combustion of fossil fuel, which produces nitrogen gases that rain out onto Earth's surface, and also owing to the application of nitrogen and phosphorus-bearing fertilizers to the Earth's surface, we have actually created a sink on land for anthropogenic carbon dioxide. Now I'd like to look at how temperature has changed over the recent past, because this is really the evidence of global warming. This shows the global average near-surface temperature. Now this is near surface. It's the global average of both land and sea surface temperature measurements based on actually going and putting a thermometer in the water. And you see the increase in temperature. It's plotted as a deviation from the 1961 to 1990 average. Over this period of time, this is the black line is the trend through the data. Over this period of time, we've had about a 0.8 degree centigrade increase in temperature, that global temperature. That is about a 1.44 degree Fahrenheit increase. Notice the Yancey event here, El Nino, La Nina. You can see it right there, 1997, 1998 El Nino. That was one of the two most powerful El Nino events that's been recorded. And that actually warmed the atmosphere somewhat. Notice the eruption of Mount Pinatubo. That actually cooled the climate for a year or two, because when the volcano erupted, it emitted sulfur dioxide into the atmosphere, into the very high atmosphere, because if you've seen pictures of Mount Pinatubo in the Philippines erupting, you know that that plume of eruption was driven right up into the stratosphere, into the higher atmosphere. And in the higher atmosphere, that sulfur dioxide reacted chemically to make little tiny micron-sized particles of sulfate aerosol. And that aerosol reflected incoming solar radiation back to space and cooled the planet slightly. So there's a competition here between the greenhouse gas warming and potential cooling owing to volcanic eruptions. Now, this is a record that commonly people don't look at in the context of global warming. This shows the stratosphere cooling. These are data from our satellites and from our balloons from about the 60s on up to past the year 2000. And what you see is a trend downward in stratospheric temperatures. And this is exactly what would be predicted from a warming of the surface in order to maintain the radiation balance of the planet. Some of this cooling, I point out, is also due to the depletion of stratospheric ozone. Note that volcanic eruptions, in terms of stratospheric temperatures, actually warm the stratosphere. Egun, El Chichon in Mexico, and Pinatubo in the Philippines led to a slight warming of the stratosphere, whereas the lower part of the atmosphere, the troposphere, cooled. Now bear with me, because I'll run through these somewhat quickly. The future temperature changes. I'll show you here in the next slide the Intergovernmental Panel on Climate Change projections for this century. Here are the CO2 emission projections, the carbon dioxide concentrations in the atmosphere, the projections, the sulfur dioxide emissions that are coming from the burning of fossil fuel that can lead to a cooling of the planet rather than a warming. This is the temperature change, and this is the sea level rise. And I'll simply point out a scenario known as IS92A, which is this black line here, this black line here, this black line here, this black line here. The IPC projections show that by the end of this century, we may be emitting to the atmosphere as much carbon as equivalent to 20 gigatons of carbon per year. That's roughly 3 times what we're doing now. The carbon dioxide concentration in the atmosphere at that time will be about 750 parts per million by volume. That's almost double what we have now. Sulfur dioxide emissions will be high. The average temperature change from the from the business as usual scenario predicts for the end of this century a 2.5 degree increase, centigrade increase in temperature over the 2000 temperature. And the sea level rise projection is about 50 centimeters above present sea level. And I won't do these. I would like to talk about some of the ocean atmosphere responses to warming, which will be addressed by the other speakers in more detail. Now, due to the anthropogenic emissions of carbon dioxide to the atmosphere, the oceans today absorb carbon dioxide. In pre-industrial times, they actually vented carbon dioxide to the atmosphere. They were a source, not a sink. So human activities have totally reversed the air-sea exchange direction of carbon dioxide for the oceans. We're putting it in now. The waters are getting more acidic. Sea level will rise, certainly, into the future. This is owing to thermal expansion of the ocean and owing to melting of glaciers. There will be increased flooding of low-lying areas, particularly like those of the Pacific Island nations, who are very concerned about the sea level rise and the possibility of enhanced storm surge. The intensity of the ocean's deep water circulation pattern, how fast the oceans circulate, might change with warming, and that could be very devastating for the climate of Western Europe. There might be changes in the frequency and intensity of natural climatic phenomena like El Nino, La Nina, which would lead, in the case of Hawaii, for a warmer and drier Pacific Ocean about us. Hurricanes might become more intense and perhaps frequent. And finally, because the oceans are absorbing the carbon dioxide, becoming more acidic, it's very likely that the calcification rates of corals and other organisms that build themselves skeletons of calcium carbonate will decrease. And I would like to point out some land responses now to the warming. Increased temperature may lead to increased photosynthesis. At the same time, respiration and decay rates of organic matter on land. The result of this, net result, is very difficult to model and predict. The precipitation changes will lead to regional changes in soil moisture and hence in plant growth, including crop yields. The CO2 fertilization effect, which I spoke about earlier, acts as a process of removing anthropogenic carbon dioxide from the atmosphere today and may actually lead to fertilization of crops. However, if the warming continues, some of the stored carbon in the forest may be returned to the atmosphere, and rather quickly, with greater respiration rates in the future. Precipitation and temperature changes. This will lead to potential shifts, geographical shifts, in plant and animal habitat and in vegetation types, and thus in biodiversity. So where do we stand with respect to the enhanced greenhouse effect and global warming? Without doubt, the greenhouse effect exists and has influenced climate change in the past. Without doubt, human activities are increasing levels of the greenhouse gases. The general consensus is that global warming due to human activities is already occurring. The major problems lie in the rate and magnitude of the warming and the effects on ecosystems. And I leave you with perhaps a little humor in what I consider a very serious situation. Thank you for your attention.
Are there questions for Dr. Mackenzie? Yes, in the back.
Can you talk about how much the melting of the tundra and its releases? The melting of the tundra and the release of carbon dioxide from there, how much will that also contribute to, what percentage would that contribute in the future?
If the tundra were to be exposed to increased oxidation because of the warming, basically, I think that's what you're saying, yeah. That could be a real burp on the order of perhaps a half or a gigaton or so of carbon to the atmosphere.
How much?
A half or a gigaton of carbon to the atmosphere. The estimates vary considerably.
Is there a question back there?
Yeah, last week I bought an issue of the New York Times, and I must say I was shocked. In the left-hand column, it explained now how some of the people are going to get rich off of the melting of the ice caps by having cruises, and actually they'll have more land to do more oil drilling. This to me really was a shock. It was in last week's New York Times.
I didn't see that article, but it would be a shock to me too.
Yeah, and they're talking about now that you can take cruises, you know, it'll be easier to get past the ice. And literally, these are cruises to see the end of the world happen. That's the way I look at it.
Well,
Do you have a question?
that's,
Oh, comment, okay.
actually, that's obviously a rather limited look at the whole problem of global warming. With sea level rise, we're going to have problems in the Pacific, including my own island of the island state of Hawaii, but particularly the Pacific Island nations of the South Pacific, because they're only a half a meter somewhere above sea level.
You have a question in the back up there?
The article in the New York Times is talking about the increased global possible trade routes, cutting travel time for commercial shipping as well as perhaps the tourist use of the Arctic and so on. It was just talking about economics. In other words, an economic lens is being used for saying, hey, global warming isn't all that bad. You have friends who have written about this in Mackenzie and so on, and that goes to that knowledge and other things. The civilization is going through.
Well, I mean, one could consider the fact that we're potentially fertilizing forests with CO2 because of the rising CO2, and potentially perhaps leading to increased crop yields as a positive effect of increasing carbon dioxide in the atmosphere. But the negative consequences of the increase of greenhouse gases in the atmosphere far overwhelm any of these, quote, positive effects, in my opinion.
We'll take one last question, but let me just remind you that at the end, at the last part of this conference, we'll have the speakers sitting at the table and open the questions from the audience again. So you'll have another chance to ask Dr. Mackenzie a question. But the lady in red.
I have a question considering the graph on stratospheric cooling.
The graph on stratospheric cooling.
I thought that I read in Nature an article that part of the problem with the stratospheric cooling measurements were due to the calibration problems. Right. And if you corrected for that, it also showed warming.
Incorrect.
Did that?
Fred, could you repeat that, please?
There's problems with the measurements of the stratospheric cooling because of the degradation of the satellite orbits. That's been corrected for, and the stratosphere is cooling.